Welcome to the deep dive. Today we're getting into something that, well, it literally holds our world together. Steel. I mean, think about it. Skyscrapers, bridges, cars zipping past, even just the knife in your kitchen drawer. Steel is absolutely everywhere. But, it's not just one thing, is it? It's this incredibly diverse family of materials. Each one is kind of engineered for a specific job. So today we're going to unpack how this essential stuff is classified, why those classifications matter so much, and what they really tell us about how steel actually performs. Our mission, as always, is to dig into the source material you've got, pull out the key bits, and give you that shortcut to being genuinely well-informed about steel.
Yeah, and what's really fascinating, I think, is how the basic recipe, the chemical composition, really dictates how the material behaves, its properties. Understanding steel classification is not just about sticking labels on things. It's more like understanding the steel's DNA. It helps predict its strengths, its weaknesses, and especially critical things like how it'll hold up under welding, for example. It's fundamental stuff.
Okay, yeah. When you look at just how many different ways steel is used, I mean, it feels like a huge, really complex topic. How do experts even, begin to sort it all out? Where do you start classifying something that's so basic but also so varied?
It can definitely seem overwhelming at first glance, yeah. But we can simplify it quite a bit by starting with two main, very broad categories. You've got plain carbon steels, and then you have alloy steels.
Right, plain carbon and alloy, got it.
So plain carbon steels are pretty much what they sound like. They mainly contain iron and carbon. Those are the key alloying elements. Now, you might find tiny amounts of other things, manganese, silicon, maybe some aluminum, sulfur, phosphorus, just traces, really. But Carbon is the star. It has this huge effect on the steel's strength, its hardness, and also its ductility.
Ductility? That's like how much it can bend or stretch before it snaps.
Exactly. How much it can deform plastically. And the outer carbon dictates a lot of that.
So even within plain carbon steel, does the actual percentage of carbon make a big difference then?
Oh, absolutely. A massive difference. We actually break down plain carbon steels even further based on that carbon content. You've got low carbon steel, sometimes called mild steel, that's typically got, say, 0.01 up to about 0.3% carbon. Very workable stuff. Then there's medium carbon steel, which is 0.3 to 0.6% carbon. A bit stronger, harder. And then you get to high carbon steel. That can range from 0.6 all the way up to maybe 1.4% carbon. Much harder. Holds an edge well. Think tools or springs.
Okay, so low, medium, high carbon. That makes sense. That covers the basics, the workhorses. But what if you need something more, something, specialized? I guess that's where the alloy steels come in. Are they sort of like the designer metals?
That's a great way to think about it, actually.
Yeah.
Alloy steels are defined by having extra alloying elements deliberately added. Things beyond just iron and carbon put in there to get specific properties that plain carbon steels just can't deliver. And we split those two based on how much of these extra elements are in there. If the total amount of these added alloying elements is less than about 7%, we call them low alloy steels. But if you go over that 7% threshold, then they become high alloy steels. Think stainless steels, for example, often fall into that high alloy category. These additions really change the game. They transform the steel's behavior, opening up, a whole new world of possibilities.
Right. It feels like we've just sort of established the main families. But I'm curious, within those, like the carbon steels and low alloys, are there even more specific types that tell us more about how they behave in, very specific situations?
Yes, definitely. We can drill down further. Let's look at some common examples within those carbon and low alloy groups and connect their chemistry to what they actually do. So some very common carbon steels might have carbon up to maybe 0.25% and manganese up to about 0.8%. These are generally characterized by, relatively low strength and okay toughness, moderate toughness. Good for general structural stuff, maybe some car body panels, things where you don't need super high performance.
Okay, the everyday stuff. Reliable, straightforward. What happens if you bump up the manganese a bit from that 0.8%?
Good question. That takes us into what we call carbon manganese steels. Here, the manganese can go up to around 1.6%. They're essentially still carbon steels, but that extra manganese gives them a significant boost in toughness. It's a relatively small chemical tweak, but it makes a real difference in how the steel resists impacts and cracking, especially at lower temperatures.
Interesting. And then what about steels for really demanding jobs? You hear about HSLA steels, right? Like for pipelines or bridges.
Exactly. HSLA, high-strength, low-alloy steels. These are pretty clever. With HSLA steels, the strength and the toughness are pushed even higher. But how they do it is interesting. It's through very, very small additions. We're talking tiny amounts of elements like aluminum, niobium, vanadium. These act as grain refiners.
Grain refiners, what does that mean?
Basically, they help create a much finer internal structure in the steel, smaller crystals or grains. And smaller grains generally mean higher strength and better toughness. It's kind of amazing, really. Just a tiny pinch of these elements and boom, you get a much tougher, stronger steel. Shows you the precision involved. A typical example you might see in pipelines or heavy equipment could be something like API 5L grade X65, or even higher grades like X70 or X80.
Wow. Okay, so tiny tweaks, big results. What about the other extreme? Steels built for really high temperatures, like in power plants or chemical reactors?
Right, for elevated temperature service, the go-to elements are usually chromium, CR, and molybdenum, often called chrome moly steels. These additions are fantastic for maintaining strength when things get hot. They also give good resistance to creep.
Creep. That's when metal slowly stretches or deforms over time under stress, especially when it's hot, right?
Precisely. It's a slow, gradual deformation. So CR and Mo help fight that. Common examples you'll see are maybe 2.25% chromium plus 1% molybdenum, often called 2.25 chrome. Or for even tougher conditions, maybe 9% chromium plus 1% molybdenum.
Okay, so CR and Mo for heat. What about the total opposite? Freezing cold, like for handling liquefied natural gas, that kind of cryogenic stuff.
For those really low temperatures, the key player is usually nickel. Nickel does a remarkable job of maintaining toughness when it gets incredibly cold, down to cryogenic temperatures. Many steels get very brittle when they get that cold. They could just shatter. Nickel prevents that. So for things like LNG tanks, you'd look at steels with maybe 3.5% nickel or even up to 9% nickel for the really extreme cold applications. It's all about matching the alloy to the job.
Now, okay, moving on. Stainless steels feel like a whole different category. Everyone knows they don't rust or resist rust anyway, but what actually makes them stainless, and how do they fit into this classification picture we're building?
Yeah, stainless steels are a big and important group. The stainless part fundamentally comes down to adding enough chromium. Typically, you need at least 10.5%, usually more like 12% or higher. That chromium forms a very thin, invisible, but tough protective oxide layer on the surface. It's passive, meaning it doesn't react easily, and it reforms itself if it gets scratched. That's what stops the rust.
Ah, okay, so it's the chromium shield.
Pretty much. And within stainless steels, there are three main families, again, based on their internal structure and alloying elements.
Okay, what are they?
First up, you have the austenitic grades. These are probably the most common ones people think of. They're alloyed mainly with chromium and nickel. Think of grades like 304 or 316. The classic 188 stainless is 18% chromium and 8% nickel. That's a 304 type. Their main internal structure, or phase, is called austenite.
And what does that austenite structure give them?
It gives them a really useful set of properties. They're good across a huge temperature range, from cryogenic right up to quite high temperatures. They have decent corrosion resistance. They're generally non-magnetic, which can be important sometimes. But they also have low thermal conductivity. They don't transfer heat very well, which means they tend to get hotter right where you're welding them. And they also have a high coefficient of expansion. They expand quite a bit when heated.
Ah, so that makes welding them trickier, more warping and distortion.
Exactly. You have to manage the heat input and distortion carefully when welding austenitic stainless steels because of those properties.
Okay, so austenitics are one type. What are the others?
Next are the ferritic and martensitic grades. Now, these are alloyed with chromium, like the austenitics, but they have very little or no nickel added. An example of a ferritic might just be a 13% chromium steel. A martensitic could be, say, 13% chromium plus maybe 4% nickel, or sometimes just carbon is used with the chromium. The ferritic grades, their main phase is ferrit, and unlike the austenitics, these are magnetizable. You can stick a magnet to them. Martensitic grades, well, their main phase is martensite. This is a very hard phase, and these steels can often be hardened further by heat treatment like high carbon steels.
So in a way, these sound a bit more like the carbon steels we talked about earlier, but with that chromium thrown in for rust resistance.
It's a good comparison, yeah. They share some characteristics with carbon and CMN steels, but with that big upgrading corrosion resistance thanks to the chromium. The downside is they're generally not great for very low temperatures. They can become brittle. But some ferritic grades are actually really good at resisting scaling that flaky oxide layer that forms at high temperatures. So you see them in things like car exhausts or furnace parts.
Okay, and the third type of stainless?
The third main group is the duplex grades. These are interesting. They're alloyed with both chromium and nickel, often in quite high amounts. Think like 22% chromium plus 5% nickel, or even 25% chrome and 7% nickel. They're called duplex because their microstructure isn't just one phase, it's a mix. It's roughly 50% ferrite and 50% austenite.
50-50, two phases. Does that make them magnetic since they have ferrite?
It does, yes. Because of that ferro content, duplex steels are magnetizable, unlike the fully austenitic ones. And that dual-phase structure gives them some real advantages. They tend to be significantly stronger than the common 304 and 316 austenitics.
Yeah.
And they also have excellent resistance to certain types of corrosion, particularly stress corrosion cracking, which can be a problem for austenitics in some environments.
Stronger and better corrosion resistance in some cases. Sounds great. Any drawbacks?
The main limitation is usually temperature range. They're generally not recommended for very low temperatures, and they also have limits on the high end, maybe around 300 and 350 degrees C, because prolonged exposure to higher temps can mess up that nice 50-50 structure.
Yeah.
So fantastic materials, but within a more specific operating window.
Okay, wow, that's a lot of different types and numbers. So what does all this classification stuff mean for someone actually working with these materials, like a welder on a construction site or in a fabrication shop? Is there a way to translate all this chemistry into practical knowledge, like a predictor for how the steel will behave?
Yes, there is. And it's a really important concept, especially for welding. It's called the carbon equivalent value, or CEV. See, the weldability, how easy and reliably you can weld a steel, is heavily influenced by all the alloying elements, not just carbon. The CEV is basically a calculated number. It uses a formula to combine the effects of the different alloying elements into a single value. And that value gives you a pretty good idea of the steel's weldability, and particularly its susceptibility to things like hydrogen cracking in the heat-affected zone next to the weld.
Hydrogen cracking, that sounds bad. Well, it leads to brittle failures, right?
It can, yes. It's a major concern. So the CEV is a kind of a predictive tool, a shorthand index for weldability.
Okay, so how do you calculate it? Is there a standard formula?
There are a few variations, but the most widely used one is from the International Institute of Welding, the IOW formula. It goes CEV equals 7 plus percent on 6 plus percent R plus percent Mo plus V5 plus percent US plus percent I15. You plug in the percentages of each element from the steel specification.
Right, okay. Looks a bit complex, but you just plug in the numbers. What's the key takeaway? What does the final CEV number tell you?
The simple rule is, the higher the CEV number, the more likely the steel is to become brittle in the area around the weld as it cools, and generally the lower its overall weldability. Higher CEV means you usually need to take more precautions during welding.
That sounds incredibly useful. So what do typical CEV numbers mean in practice? Like, what precautions are needed?
Okay, let's break it down based on typical ranges. For common mild steel, the CEV is usually less than 0.4. These steels are considered readily weldable. You generally don't need to preheat the metal before welding if you're using what we call low hydrogen welding processes. Now, if you have really thick sections, or the joint is under a lot of stress or restraint, or if your welding process might introduce a lot of hydrogen, then some preheat might still be advisable even for mild steel.
Okay, below 0.4 is pretty straightforward. What about the next step up, those CMN steels or some low alloys?
Right, for carbon manganese, medium carbon, and many low alloy steels, you might be looking at a CEV between, say, 0.4 and 0.5. With these, if the metal is thin, you might still get away with no preheat. But as it gets thicker, you'll definitely need some preheat, maybe a low level like 50 or 100 degrees C. And using low hydrogen welding consumables and processes becomes much more important here to avoid cracking.
Got it. And then the really high carbon or more heavily alloyed steels, where the CEV goes above 0.5, sounds like that'd be tricky.
They definitely require more care, yes. For steels with CEV over 0.5, you're almost certainly going to need significant preheat, sometimes quite high preheat. This slows down the cooling rate after welding, which helps prevent brittle structures from forming. Using low hydrogen processes and consumables is mandatory, basically. No shortcuts there. Sometimes you might even need post-weld heat treatment, heating the whole weldment up again after welding to relieve stresses and soften the structure. And you'll want to control the cooling very carefully after welding too. No quenching it quickly. Slow cooling is key.
So that CEV number really dictates the whole welding procedure, doesn't it?
It's a critical guide, absolutely. It helps predict the risk. And understanding the steel type also tells you what kind of problems you might encounter. Things like hydrogen cracking in the heat-affected zone, or maybe solidification cracking right in the weld metal itself, or lamellar tearing in certain joint designs, or even weld decay in some stainless steels. The classification points you towards the potential pitfalls. We don't need to go into all the crack types now, but the classification is the first step in knowing what to watch out for.
Wow. Okay, we have definitely covered a lot of ground today, from, basic plain carbon steels right through to those complex duplex stainless types. And seeing how something like that carbon equivalent formula can condense so much chemistry down into practical advice for welding, that's really something. It's almost like a cheat sheet, isn't it? To avoid making a really costly mistake when you're joining these materials.
It is a powerful tool, and it really makes you think, doesn't it? Knowing just how complex even supposedly simple materials like steel actually are, and how tweaking that composition just slightly changes everything, its strength, its corrosion resistance, how easy it is to work with. It sort of raises a question for you listening. How might this deeper understanding of material composition change how you look at or interact with materials in your own life, or maybe in your work?
That's a great point. So maybe next time you cross a bridge or look up at a skyscraper or even just pick up a stainless steel fork, take a second. Think about the hidden complexity, the incredible engineering that went into choosing just the right type of steel for that job. Understanding its classification, as we've explored today, is really the first step to appreciating the design, the science, and the sheer utility packed into that piece of metal.